Well, this is part 2 of the periodic table test review questions. I think I got through, just started on number 14 before my flash drive went out. So let's see. So back over here to number 14. Let me zoom out, get this adjusted. So number 14 said, which are the second period elements? Okay, we did that. And we were just talking about what are the group 14 elements? Well, when you look on the periodic table, 1, 2, 3, 13, 14. Group 14 is right there. And so you could just list the symbols for those elements. Now on this one here, because I want to save time, I don't want to be spending too much time writing all this stuff out. So first off, let me just kind of go over these. What's atomic radius? Let me zoom in. So if you're watching this on your little tiny electronic phones, atomic radius is the size of an atom in angstroms or picometers. Okay, now we in class we graphed in angstroms, but the book tends to use picometers. It's just like 10 to the minus 12 or something. Anyway, it's really a small size. So it's just telling you how big these atoms are. And a lot of times, yeah, so there we go. That's how big the atom is. Now, ionic radius, when the atoms have ionized, when they've gained or lost an electron, it's going to be just the size of the ionized atoms. Okay, so metals tend to get smaller when they ionize. You know, they'll tend to be a little bit smaller, where so metals to metals will ionize and get smaller. Non-metals will ionize and get bigger. We'll cover that in a little bit. But anyway, ionic radius is just the size of the atoms when they've ionized. Now over here, the next one, electronegativity. Now electronegativity is the ability to attract an electron. And the elements over in period on the right side of the table, they really want to attract electrons. These guys really need electrons. They're going to have high electronegativities. Fluorine will have the highest. As you go down the chart and to the left, electronegativities get smaller. And it's important to note that for electronegativities, the highest ones are going to be the halogens, and the lowest are going to be the noble gases. The noble gases do not need to attract any electrons, so their electronegativity is 0. They have no electronegativity, so fluorine would be the highest, and as you get over here, it gets lower. Ionization energy. Slide this guy over. So ionization energy is the energy needed to remove one electron from an atom. Now, and actually ours, you might modify this. This is first ionization energy. You don't need to worry about second or third. So these elements over here on the periodic table, these guys, if you try to move an electron from them, they do not want to give up their electrons. They need more. They're holding on to the ones they have tight. These elements over here want to get rid of electrons to become stable. They're almost throwing their electrons away. So very low ionization energy. Energy, again, to pull an electron off. And when you pull an electron off, you're ionizing it. Number 16, what are the trends for atomic size as you go across or down the table? Well, let's see, as you go across the table, what happens is they're really big on the left side and they get smaller as we go across. That's the symbol. So what we're going to say is as you go across the table, they decrease in size. As you go down the periodic table, okay, so you start they get bigger as you go down, so their size increases as you go down. We've got this graph right here at the bottom of your paper. Now, first off, we're going to go across the first one's to go across a group, across a period. So you go across the period, they get smaller. You're getting more protons in the nucleus. It pulls the shell in. Then they reset when you start to a new shell, because now they're going to be bigger, but then as you go across that period, they start to get smaller. So you get this repeating pattern. There's always these hiccups in there. So that's how I'm symbolizing that. Why does atomic size change the way it does? Okay, so why does it get smaller as we go across? And as atomic number increases, okay, so as you go across the periodic table, atomic number is increasing, which means you're getting more protons. So as the atomic number increases, that's what that means, so does the strength of the nucleus. So by that I mean that the nucleus is gaining more positive charge. So So as the atomic number increases, so does the strength of the nucleus as it gains more plus charged protons. More protons in the nucleus, this pulls the electrons closer together. So that's why atoms, when you come across the table, we're getting more and more protons, they're being pulled in closer and closer. Number 18, which group of elements are the peaks for atomic size when graphed, and which are the lows? Well, when we're graphing this, it turns out the very biggest elements are going to be the alkali metals. Those are the metals, the elements in group 1. So these atoms over here are the biggest in their period. And then the smallest atoms, because the trend gets smaller, it's going to work out the noble gases will be the smallest elements in their period. So that'll be noble gas. Let me get it so you can see it. So for atomic radius, and it'll even work out for ionic radius too, the noble gases. Well, actually, noble gases don't ionize, so they're not going to have an ionic radius. So there you go. Number 19. What are the trends for electronegativity? Well, electronegativity is going to, as you go to the right side of the table, it'll get bigger. As you go down the table, electronegativity decreases. And when you look on the table, on the periodic table, so when we draw this out, I'd always like to put X's through the noble gases. They do not need to attract electrons. That's what electronegativity was, and you go back to question 15. So noble gases do not attract electrons. So the highest one's going to be fluorine. Fluorine is closest to the nucleus. The electrons are closest to the nucleus, really pulling it tight. And as you go down the table, you end up here with the lowest element, the lowest electronegativity. Again, metals don't need electrons. They tend to get rid of them. Number 20, why do electronegativity values change the way they do? Okay, metals don't need more electrons. Nonmetals really do need more electrons. Oh, I guess I should have put more electrons. There we go. So they pull them in. They tend to attract more electrons. So nonmetals are going to attract electrons. Metals don't need them. Which group of elements are the peaks for electronegativity? Oh, hey, by the way, I think I told this only to my period 7 class. This graph's a little off. We need to draw a line across here. We need to reset this to 0. Sorry about that. And then 1, 2, 3, and 4. Okay? So we're going to label right here. At 0 are the noble gases. Noble gases have no electronegativity. The highest, the peaks on this one are going to be the halogens, okay? Because the halogens really need electrons, so they're going to have a higher number. And I think I just answered number 21 on there. Number 22. Move that over. You can hit pause if you needed to go back. So number 22, zoom out a bit. What group of elements are not included in the graph of electronegativity? Why not? Well, often noble gases aren't because they have no electronegativity. This one here, we plotted them as 0, but they don't need electrons, so they do not attract them. Again, electronegativity is the ability to attract electrons. Number 23, what are the trends for ionization energy? We said that's the energy needed to pull an electron off. Well, as you go across from left to right, the ionization energy increases, so whether you like an increasing arrow, or I've drawn a graphic here to show it's getting bigger as you go to the right. As you go down the periodic table, it gets smaller, okay? So as you go down to period 6 and 7, it doesn't take much energy to pull an electron off. And the elements, what has the lowest ionization energy? It's going to be these elements down here, right there, and probably cesium, because francium doesn't exist except for fractions of a second. So we'll say cesium or francium, but it's usually the bottom left corner of the periodic table. So I put cesium or francium down there. Number 24, what group of elements are the peaks for ionization energy? Okay, well, let's take a look at this graph right over here. So let's label this ionization energy. The tops are noble gases. The peaks are noble gases because it is possible to pull an electron off of a noble gas. It's just extremely difficult. It's like, why bother? But it is possible. And then at the bottom of the ionization is going to be the alkali metals. Because the trend is, when you're an alkali metal, you've got it's really easy to ionize, to pull an electron off. As you go across over here, it gets hard. So the energy gets bigger and bigger and bigger over here. So alkali metals are the bottoms of these charts. Noble gases are the top. 26. What are ions? They are atoms that have gained or lost electrons. They do that so they can become stable. How do ionic sizes compare with atomic sizes for positive or negative ions? Well, metals will form positive ions called cations. I make the T really big. Nonmetals will lose electrons. Okay, so, oh, wait a minute. Nonmetals will gain electrons, and when they do, they become a little bit bigger on there. They call these anions. I always make the cross on the A really big. These are called anions. But when a nonmetal ionizes, this electron that it's probably taken from this guy makes the shell a little bit bigger. That's just the way it is. What are the number of electron? How are the number of electron shells determined? It's the same as the period number. Whatever the period the element's on, that's what it's going to be. How many electron shells do neon and nitrogen have? Well, neon and nitrogen, they are both. There's neon, there's nitrogen. They are, there's neon, there's nitrogen. They're both in period 2, so they have 2 shells. What are valence electrons? Electrons on the outer shell. Okay, they're the outermost electrons. How many valence electrons do aluminum and bromine have? Well, it comes down here. Let me back up to this one first. How many valence electrons do they have? Well, group 1, they will all have 1 valence electron. Group 2, they have 2 valence electrons. That's why they're in group 2. Group 3-teen, 3. Group 5-teen, 5 electrons, 5 valence electrons. Group 18 will have 8 electrons with the exception, moved off the table here. So group 18 has 8 with the exception of helium. Helium is so small it only has 2 electrons. So coming back over to here, how many valence electrons do aluminum and bromine have? Well, aluminum is in group 3-teen, as I like to call it, so that means it has 3 valence electrons, and bromine is over here in group 8-teen, so it has, wait a minute, my mistake, stop. Bromine is in group 7-teen, so it has 7 valence electrons. How many neutrons are in each atom? I'm not going to calculate all these for every one of these, but I'll show you the trend. So when you get this format, this is showing you the mass number. This is usually how they'll show isotopes. This will tell you the atomic numbers, kind of opposite what we're used to. But for neutrons, you subtract. So it's going to be 16 minus 8. Bromine, 80 minus 35. Okay, you get the trend. There, you can do that. Now, here's something that is going to be on the test, and we just forgot to put on the review sheet. So I'm calling this question 29. How many electrons are in lithium ion and nitrogen ion? So first off, what you got to ask yourself, if an element has ionized, which means it's gained or lost electrons, if it has a positive charge when it's done, you got to ask yourself, has it gained a negative electron or has it lost a negative electron? Well, if the charge is plus here, this one has had to have lost an electron. And my little memory clue is if it's lost an electron, it'll end up with a plus charge. Duh. Okay, but anyway, normally lithium, which is atomic number 3, will attract 3 electrons. But if it's lost 1 electron, because it'll lose 1 electron to be stable, so 3 electrons, I'm going to subtract 1 electron because it's lost 1 electron. It'll now have 2 electrons. Because it only has 2 electrons, it still has 3 protons in its nucleus, so that third proton gives it that plus charge. Now, over here, we've got a nonmetal, and nonmetals will have negative charges when they ionize. So this one has, what's going to happen is, since it's got a negative 3, it had to have gained 3 negative electrons. So it gained electrons. Now, I like to say that negative. So if it's got a negative ionic charge, it's gained. Okay, hopefully that works for you. Anyway, normally, nitrogen over here, nitrogen normally has 7 protons. Well, it always has 7 protons. Normally it'll have 7 electrons, but it's gained electrons. And actually, since it's got a negative 3, it's gained 3 electrons. So 7 electrons plus 3 electrons will equal a total of 10 electrons in there. So that works. Number 30, almost done here. Carbon 13, that just tells you the mass number for this carbon isotope is 13, fluorine 20, beryllium 11. What I recommend, just think of it like this. Every carbon has 6 protons, so I just kind of made periodic table squares. But instead of putting the average atomic weight, as you would find on the periodic table, I just put the new mass number, 13 for carbon 13, 20 for fluorine 20, and for beryllium 11. Now, okay, that will tell you number of protons. That will also tell you number of electrons, the atomic number, and you still have to subtract 11 minus 4 to find out how many neutrons for each of those, well, for the appropriate ones. Let's see, the basic trend, atomic radius. As we go across, so atomic radius, atoms get smaller as we go across. So if this is atomic number right here, as we go across a period, they're going to start big and they're going to get small as we go across. That's the basic trend as you go across a period. Okay? And then on this chart right here, you can draw like this, make them small, but as you go down here, they get bigger and bigger as you go down a group. Ionization energy. It's harder to ionize elements as you go across the table. So this trend is going to be the opposite of atomic radius. So what happens here, I tend to use E's here, so as you go across, the ionization energy increases and increases. It's highest with the noble gases. The noble gases do have ionization energies. And then as you go down here, these guys get even smaller, till you can hardly even see it there. So that helps. Electronegativity is going to be the same trend as ionization energy. It's going to get, as you go across the period, it gets bigger and bigger. But when you get to the noble gases at the very end, it drops to 0. So, electronegativity is what drops down to 0 when you get to the noble gas down there, okay? Now, on this chart, I'm just going to put X's here just again to remind me that for electronegativity, the noble gases, which would be sticking up right over here, they don't have any. Fluorine, our friend fluorine, right there is going to have, actually I guess these would have been the noble gases. I guess I can cross those off. Sorry, don't be mad at me. So fluorine right here has the highest, and then down here cesium will have the lowest. And as we did in the alien periodic table, the most active nonmetals. Okay, so, well, these nonmetals are not active. Fluorine is the most active nonmetal. High nonmetal. Highest nonmetal activity. So the most active nonmetals are up here. Down here is where we're going to have the most active metals. So let me see. The most active metals are right there. The most active nonmetals right up there. I'm done. I'm out of here. Goodbye. Toodles.